video, I want to look at an example problem making use of the simple harmonic motion principle that we discussed in the last video. So in this problem, we're going to examine a pendulum. And this pendulum is simply a mass at the end of a rope or something like a chain or any sort of straight, inextensible material. And if we disturb that pendulum by some small theta such that we move it out of its equilibrium position, which would be hanging in the center here, then we can evaluate what would happen as a result of that small disturbance. So what we're going to try to find then is a general purpose calculation for the period of oscillation for this pendulum. And I like the pendulum as an example of simple harmonic motion because it's different from the setup that we used, where we had a mass suspended from a spring, and therefore allows us to look at the problem in a slightly different way. So if we displace the pendulum by some small angle theta, our first step is to draw a free body diagram to kind of come up with what our setup at this point would be. So if I'm displaced by some small amount such that the tension that is in the rope pulling the pendulum is applied at an angle rather than straight up and down, it would look like that. And then my weight, which is equal to mass times gravity, is pointed down. Now we can represent our angle theta on here like this. So the displacement of the pendulum is realized in the orientation of the weight of the mass relative to the normal direction which applies to the rope. So I'm going to orient a coordinate system using tangential and normal directions in order to kind of write my equations. Now previously we talked about anytime there's some disturbance which moves my system out of equilibrium, there's going to be a restorative force which is trying to bring that system back into equilibrium. So in this case, my restorative force is the component of my weight which is pulling the mass in the tangential direction back towards its equilibrium position. So therefore, I'm going to define my restoring force as Ft, and it's going to be equal to the tangential component of that weight. So I'm representing weight as mg and then sine theta. So now, if I take a summation of forces in the tangential direction, I can say that I have mg sine theta, so again, the tangential component of the weight, and that's going to be equal to the mass times the tangential acceleration of my pendulum. Now, over here on my picture, I've defined some geometry for the pendulum, and that is that if it is displaced by an angle theta and the rope attached to it has a length L, there is an arc length S, which is going to be equal to L theta, which we've seen before in curvilinear motion and things like that. So this arc length that the pendulum travels between equilibrium and its current position would be equal to L theta. And therefore, I'm going to define my tangential acceleration as the second time derivative of S. So the second time derivative of the arc position. And as I just mentioned, S is equal to L theta. So therefore, if I put those two things together, I get that the tangential acceleration is equal to L theta double dot, since the length does not change. So now the reason this is useful is that I can rearrange my summation of forces equation to have everything in terms of theta. Therefore I have minus mg sine theta is equal to mat, which is equal to m L theta double dot. So I can see right away that I have mass on both sides, so I can cancel that out. and I get minus g sine theta equals L theta double dot. And I can rearrange this equation into the standard form as theta double dot plus g over L theta equals 0. Now the reason that I want to rearrange this into standard form is because recall that previously we said that the standard form equation could also be written as x double dot plus the natural frequency squared times x equals 0. So if we take that same principle and apply it here, that suggests that the natural frequency is equal to the square root of g over L. Because I know that my equation must have that form where omega n squared is in the position where it's multiplied by theta. Therefore, I can solve for the period tau, recalling that it's equal to 2 pi over omega n. And that gives me that tau is equal to 2 pi square root L over G. So that's a nice general solution which gives me the expected period of oscillation. Now, the kind of interesting thing that comes out of that result is that you might notice that the only variables in there are L, which is the length of the rope, and G, which is the acceleration of gravity, so that's a constant. And therefore, my period of oscillation is only dependent on the length of L. It doesn't matter what my mass is, and it also doesn't matter how much I displace my pendulum. Theta doesn't show up in that equation. So by this solution, my period of oscillation is only dependent on how long the rope is that is attached to my mass. All right, thanks.